So let me remind you briefly where we were yesterday. When we stopped, I sort of went quickly through the arguments of how you move from general fluid equations, hydrodynamics equations, to actually the primitive equations of meteorology, which are the equations that are satisfied to leading order on large scales in a stably stratified atmosphere. Then I mentioned some of the waves that are obvious coming out of this system of equations, Rossby wave, gravity waves. I mentioned a couple of instabilities that are known to emerge from this system of equations, one being barotropic or shear instability, and then the other one being the baroclinic instability. We're not done going through sort of basic principles here before I discuss application. I want to get to that today. And so another thing we want to spend time, a little bit of time on is this concept of a dimensionless number. They are quite useful to understand the general regime of flow or dynamics you might have in a system. And so three numbers of interest for atmospheric flows are the Rossby number, the Rhine scale, which if you it's actually a dimensional scale, but if you typically scale it by the planetary radius, you get a dimensionless number. And the Rossby deformation radius, which is also a scale with some unit like meters, if you will, but again, if you scale it by the planetary radius, you get a dimensionless number. You're probably familiar with this concept of and the usefulness of dimensionless numbers in hydrodynamics. The most famous, maybe, dimensionless number that people mention often in hydrodynamics is a Reynolds number, which is a nice dimensionless number that allows you to discriminate between a laminar flow regime, typically in a pipe, flow in a pipe, in a viscous fluid, and a transition to turbulence at a high enough Reynolds number, something like 2000. And the way you get that number, if you might, that's interesting. My computer is stuck. Let me unplug. Okay. So let's see. All right. Seems to work. Yeah. So the way you get the Reynolds number is basically simple dimension analysis between the acceleration term here and the viscous term, let's say the shear viscosity term here. You do the dimension of these two terms, and then the ratio of the first to the second is basically how you get the Reynolds number. So you can and so this is exactly how you get the Rossby number. Now looking at the primitive equation of meteorology. And the way you do it is you basically do the ratio of this, again, acceleration term to the Coriolis term here. And when the Rossby number is small, then, so if you, I sort of keep telling you to neglect that term, so I'm going to ask you again to say, let's neglect that term, it's not dominant. And so if you get a small value of this acceleration term relative to the Coriolis term, then you're only left with two dominant terms that have to be nearly equal in the force balance, in the horizontal force balance, and that's Coriolis force balancing pressure gradient. And so that's actually known as geostrophic balance. And so the Rossby number, this first dimensionless number here that we're discussing here, is actually telling you first how important rotation is in controlling the flow dynamics. The smaller the Rossby number, the more important the rotation is in controlling the atmospheric flow. And actually, in the limit of a small Rossby number, you actually do get to satisfy away from the equator, typically geostrophic balance. That's the case, for instance, for the Earth. And so it will be interesting for us to look at exoplanets and actually compare their Rossby number to to solar system planets, for instance, and we can learn something about the general dynamical regimes we are in. So two other numbers that are maybe less obvious, at least first time I met them, they were less obvious to me, is the Rhine scale and the Rossby deformation radius. So I'm not going to go through how we derive those numbers. I'm going to give you some references at the end of the lecture today, textbooks. There's a very good textbook by Vallis, Jeff Vallis. I really like that textbook about the dynamics, so you can get everything derived properly in that textbook. But I'm going to emphasize maybe the meaning of those numbers. So the Rhine scale is actually a scale that's trying to understand to what extent the change in the Coriolis force with latitude is actually affecting the flow. And the practical consequence of that, the practical application of the use of that number is to actually define a typical banding scale. And so if you look at Jupiter and Saturn, you see from the clouds the banding of the flow, tracing the actual atmospheric motions. And the number of bands you get on Jupiter and Saturn is typically associated to the value of the Rhine scales. Basically, it's a number that tells you how banded your circulation might be. And so that's quite a useful number to know about. And then the other interesting number that will tell you something about the dynamics of the flow is this Rossby deformation radius. It plays a very important role in, well, in various things, actually. For instance, you can look at it as sort of a causality scale. This is a larger scale on the sphere beyond which you expect the flow to lose causality. And meaning of it is just like over a rotation time scale, basically how far can a sound wave propagate. And then beyond that, you don't expect the flow to be really causally connected if rotation is important for that flow. That's one way to think about it. And so the effective use of that scale, that at least that I'm familiar with, is to say that's typically the largest size of the vortices you can expect in your flow. It's also typically the size of the fastest growing baroclinic mode in a baroclinic instability. So it's actually quite an important number. And a typical demonstration of how those scales manifest in a flow is in a free turbulent simulation. So people can actually simulate two-dimensional turbulence on the sphere just in one layer, and then starts with seeding a lot of turbulence on small scale. And because 2D turbulence behave with this inverse cascade that we heard mentioned yesterday, where energy goes to the larger scales, what you actually typically achieve is actually the creation of bands of winds that go east-west in an alternating manner. And then typically the existence of a polar vortex. And the typical number of bands you get is related to the value of the Rhine scales in that simulation of the 2D turbulence on the sphere. And the size of the vortex that you can achieve is related to the Rossby deformation radius. So that's a typical application of those numbers. Yeah.
So if you have a hot Jupiter with force on a global scale, presumably the Rhine scale banding must break down. That's more on the small scale turbulence and baroclinic instability. But I can imagine if you use a hot Jupiter close, it's got some other distribution that may break up that band.
I partially agree with that. I think you're right about the forcing being large scale on the hot Jupiter, and that being an important factor affecting their dynamics. My personal view on the Rhine scale is that, in fact, the Rhine scale or the Rossby deformation radius do not have to be associated to baroclinic instability. The example I just gave is that just freely decaying turbulence, actually, they do emerge naturally from that. So they can affect the evolution of the flow through an instability, but there seems to be more general principle of this causality scale, and there's this limit to the banding you can get. That's my understanding, at least, if someone wants to comment on this. And so what's interesting about this is that you're going to get to see now in a few slides down is that the typical regime we are in for exoplanets, for which we have data, tends to be in a regime where the rotation is not super important and those scales are large. They're planetary in size. And that's because we are dealing with slowly rotating planet. And the reason we're dealing with slowly rotating planet is because they tend to be tidally locked. And well, astronomers tend to find planets that are close to the stars. They're tidally locked, and as a result, this rotates slowly. So this is sort of the general regime that has been probed so far in terms of exoplanets that have been, I would say, observed through a variety of infrared or optical measurements. And so we can look at this in a bit more detail, if you will, through this table. This is a little bit of an old table from half a decade ago now, from a review, and it's basically comparing this some of these key numbers for solar system planets and a number of extrasolar planets, mostly hot Jupiters. There may be a hot Neptune in there, but they're mostly hot Jupiters. And so the first thing to, and maybe the way you want to compare things here is to really compare these extrasolar planets and hot Jupiters to actually the giant planets in the solar system, and maybe most directly to Jupiter and Saturn here. And so the first thing to notice is that assuming those hot Jupiters that are really close to the stars are indeed tidally locked, so that we know their rotation rate to be their orbital period, which is of order just a few days, actually they rotate rather slowly. They're slow rotators, something that I was just mentioning. The other thing to notice that's actually dramatically different is that in watt per square meters, the fluxes you receive are actually many orders of magnitude larger. So they're strongly radiated, slowly rotating planet is what these hot Jupiters are. The equilibrium temperatures are not in the 100 degrees, they're in the 1500, 2000 Kelvin, so very hot regime, which in fact might bring up new physics, one of the things I'll discuss in tomorrow. Yeah? So you can just do order of magnitude, you can assume isothermal, say, right? So an isothermal atmosphere, you know the stratification, and that's a typical scale, yeah. So I think that's what was done here, yeah. That's what we did. So then looking at those numbers that I just mentioned, you know, the Rossby number, the Rossby deformation radius divided by the planetary radius. A here is actually not the semi-major axis. Astronomers tend to use A for that. It's actually the planetary radius. And then the Rhine scale divided by the planetary radius. And so on Jupiter and Saturn, you get strong rotational control of the flow, small Rossby number, much less than 1. And then you get a small Rossby deformation radius and actually a relatively small Rhine scale. And the inverse of that Rhine scale multiplied by pi, something like that, is typically the number of band that you expect, east-west banding that you expect in the flow. And so looking at now the hot Jupiters, notice that these two of these numbers you don't know a priori because you need to know the wind speed. There is a U scale. If you look at my slide here, you need to have a typical velocity scale to actually define those numbers. I guess I didn't spend the time telling you exactly what goes in this. So the Rossby number is a wind scale divided by the Coriolis parameter divided by the planetary radius. The Rhine scale is the square root of this wind scale divided by the latitudinal gradient of the Coriolis parameter, this F. You take the gradient in latitude, and you get actually this beta parameter. And then the Rossby deformation radius is a Brine-Weisseler frequency that tells you how stratified your atmosphere is, or in other words, it's related to the gradient of entropy, or gradient of temperature, if you will, as a function of pressure in your atmosphere. And then H is a special scale height, and F divided by F here is again the Coriolis parameter, 2 omega sine phi. So not knowing a priori the wind speeds on those planets, you have a range of possible values here for the Rossby number and the Rhine scale. But the thing you'll notice is that the Rossby number is basically approaching unity or slightly less than unity for a wide range of plausible velocities. And similarly, the Rhine scale is approaching unity or exceeding unity. The Rossby deformation radius is also approaching unity, and that's in comparison to Jupiter and Saturn, which are fast rotating planets. So again, because we have slowly rotating planets here, the conclusion is that rotation is significant. You still have a flow that's rotationally controlled, but not as much as on Jupiter and Saturn. You can expect just few bands, so that's what I've highlighted here, and large-scale features. If you form vortices, they might be very large in scale, about comparable to the planetary radius. So this is a general regime we're expecting here that's rather different from the giant planets in the solar system. Now going back to the discussion we had yesterday about the wind speeds, which this is one of these big unknowns in the business, is and sort of a point that was made by Dave. You can see actually the scaling of velocities here from inside to outside in the solar system. So of course the terrestrial planets here and Titan to some extent have this big difference is that they have a planetary boundary layer. So they have drag applied at the bottom from the surface. And maybe on Venus, it's somewhat less obvious because the atmosphere is very thick. So how much of that drag is felt by the upper level of the atmosphere is maybe less obvious. But going to the giant planets, you know, the less flux they receive, almost, the faster the winds go. So the less forcing, the faster the winds you get. So it means the less friction there has to be somehow. And again, this is a zeroth order problem that is not solved for the solar system planets. And so then we have to then look at the hot Jupiters and try to guess what might be happening. And certainly what we know, the naive expectation might be the following. The forcing is much stronger. See, the forcing in terms of the amount of energy you receive per second that potentially is there to force your winds is orders of magnitude larger. Because these are gas giant planets. Structurally, if you will, friction mechanisms you might think might be similar than the giant planets. That would be the first naive way to think about this. Probably not very good, but as a first guess, it's a good starting point. So you might expect them to get very much faster winds. How much faster, it remains to be seen from actually trying to solve those equations on the computer. You will see through the lecture today that something, a word that's emerging again and again and again is super rotation. So I thought I would just put a slide on that to make sure we are on the same page on the significance and the meaning and significance of this. So by definition, east is in the direction of rotation on a planet and west is in the opposite direction of rotation. So we talk about an eastward wind. It means a wind going towards the east, and it's a wind going in the same direction of the as the rotation of the planet. And so the significance of super rotation is the following. I'm looking for the, I guess I'll do it in color. Shall I move that here? It's good here? Yeah. So the way we want to think about this is just we look at this hemisphere. I have this planet here, and then this is my omega vector, the rotation of the planet. And I want to look at it now from not being sitting on the planet, but from an inertial frame. You know, just I'm looking at this planet rotating. And if I look at this layer of fluid here, I'll say it's in solid body rotation. The fluid, it might be actually a good starting condition for trying to simulate what's going on this planet. I'm going to say I have a bulk rotation of my interior of the planet. It would be the solid on a terrestrial planet, for instance, or the bulk convection zone on a giant planet. So I have this reference rotation here. And then my atmosphere is in solid body rotation if everywhere the wind speed is matching the angular velocity. So I have my atmosphere that's rotating uniformly. Everywhere the velocity vectors is actually eastward at the same speed as the planet is rotating. In other words, if I go in the frame rotating with the planet, I have zero velocity. It's an atmosphere at rest rotating with the planet. Okay, so that's what I call solid body rotation. I see some puzzlement here. Shall I try that again? Does it make sense what I call solid body rotation? Yeah, okay. So then if you ask yourself, what's going on with angular momentum in that atmosphere? So again, looking from an inertial frame here, my angular momentum, I'm going to write angular momentum vector here is going to be the product R times P, where P is mv, the momentum, linear momentum. If I can do it by unit mass, so I divide by unit mass, the parcel of particle is R cross V, where R really is a cylindrical vector, cylindrical distance away from the rotation axis, okay? And so, because I'm in solid body rotation, that's what I start with here for the sake of demonstration. It means that I have everywhere the same velocity, which is the velocity given by the global omega of my planet. And so I have a maximum of angular momentum at the equator, just because I'm further away from the rotation axis. So if I ask, now an atmosphere that is at rest, meaning rotating with the bulk planet, has actually a maximum of angular momentum at the equator, and because as you go on an isobar, say, you go closer to the rotation axis, I have less and less and less and less angular momentum as I go away. Okay, so this is just setting up the condition here for the slide. Now I'm going to move that away. And so then the natural expectation is pretty simple. Okay. Then the natural expectation that one would have is that angular momentum will flow down gradient. The meaning of that is that angular momentum will flow from the maximum of angular momentum to a minimum. Why is that a natural expectation? For instance, if you have anything that works like a viscosity, this is the way typically you would expect it to go. So now what is referred to as superrotation is actually somehow angular momentum flowing up gradient. So somehow you have a maximum of angular momentum here. You start with solid body rotation. You have a max of angular momentum at the equator. The atmosphere starts going. You shine on the atmosphere. You start driving atmospheric flow. And somehow you actually pile up angular momentum here at the equator where you already have a max. This seems a bit unnatural. For instance, if you consider what viscosity would do to that flow. And so that's the meaning of superrotation. It's a non-trivial feature of an atmospheric flow where somehow you pile up angular momentum where it's already at the maximum. And then now going back to the description of what we see in the frame of the rotating planet, it means it means a positive eastward wind at the equator. That's a sign of superrotation. Now there is a theorem from the 60s due to Hyde. Yeah. That might be. So what I'm referring to is what equatorial superrotation, yeah. Yeah. I mean, I guess you could generalize that argument, yeah. And so there's a theorem from the 60s, the late 60s, I think, from Hyde, who shows that actually you cannot achieve superrotation. This is why it's non-trivial. You cannot achieve superrotation with a purely axisymmetric flow. It's a pretty strong theorem. If you think that everything is axisymmetric in your atmosphere, all the motion, let's say a Hadley circulation, it's a meridional circulation that in first approximation is actually axisymmetric, you cannot achieve superrotation through that. Somehow you need to invoke non-axisymmetric patterns in your atmospheric flow to achieve superrotation. So when you see superrotation, you know there's something going on that has to do with non-axisymmetric features, somehow converging angular momentum where the max of the angular momentum is already. And so it's a non-trivial feature. And this non-trivial feature is emerging all over for extrasolar planets. So it's a rather interesting topic here. No, it's totally possible. It's not possible. It's not possible with an axisymmetric. Oh, I guess I would recommend you look at the derivation of the theorem, maybe. On top of my head, no, I'd rather not do that like this, yeah. 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 Even though the anti-dynamo theorem is strictly 2D, and actually this is not strictly 2D, so I don't know how far you can push the analogy. Right? The anti-dynamo theorem that I'm aware of is actually strictly 2D. Oh, okay. So I didn't know that. Yeah. I thought it required strict 2D. If you add a third dimension, you lose it. No? Okay, well, it's getting to be technical. Yeah, this is not, even when you solve primitive equation, it's not strictly 2D, so I'm not sure anti-dynamo is exactly the analogy. But maybe the generalization of it, yeah. Andrew? No, so when I say positive, this is, I have two frames of reference here, so yeah. When I say positive speed, then I go in my frame on, my non-initial frame on the planet. I'm sitting there and I say, I have my winds, positive means eastward. So it's going beyond the rotation of the planet, right? It's like, yeah. So typically what you expect, what you see achieved on the Earth is actually negative speed, negative eastward speed here at the equator. And again, you'll see, I'll show you many zonal wind patterns for exoplanets, and they exhibit superrotation. So that's why I'm spending time on this. Okay, I'm almost done with this. I'm sort of done with the description of general principles. We can discuss applications soon. I just wanted to have a few words about solvers so that you have an idea what's sort of behind all these applications I'll describe. It's, you could give a whole lecture on just the solvers themselves. I think Jonathan mentioned that already. A lot of what has been done is basically take Earth-centric general circulation model, or sometimes they call global circulation models, GCMs, and modifying them, making sure that people have not hard-coded the Earth's gravity or the Earth's rotation rate, but they're actually really general. Some of those GCMs you cannot use because it's really hard-coded there. 9.81 was divided by pi or something, and then you just don't want to touch those codes. But there is actually a lot of codes that are open source, that are actually quite general, that people have been, and people have been successful at modifying them and adapting them to study exoplanets. So these are codes, you know you can go with that, and it works. And so there is a list here. I'll go through it briefly. There is various approaches to solving this primitive equation of meteorology, and actually all the auxiliary equations that come with them. But typically, they fit into a finite difference, finite volume, or spectral methods. So you take the primitive equation of meteorology, and then if you just look at the derivative, you difference them, that's a finite difference, something that I think most people are familiar with. Finite volume are in some sense better because they don't look at the weak version of the conservation laws. They actually look at integral forms. They try to satisfy integral forms over some volume of those differential equations. And so they have actually maybe better conserving properties. They might be a bit more difficult to code, but they have these advantages. Spectral methods are basically decomposing this equation into normal basis of Gaussian Legendre polynomial. You can want to think about Fourier transform, so mode in spectral space on the sphere specifically. And they have a lot of advantages, some disadvantages. One of the advantages of the spectral method is that the pole is not special. And so that's really nice because all of the other grid-based method, whether they're finite difference or grid-based, they have issue with the pole that, if you imagine drawing a grid, you get very, very, very small grid as you approach the pole. If you have a simple grid, the simplest way you might do a grid, in fact, I think I have a picture here. You see, they removed it here. That's very convenient, right? But if you think going all the way to the pole there, you're going to get a very, very, very small grid. And then you have a problem there because you generally don't want things to happen on very fast time scale in a solver, and when you have very, very small grid, that leads to numerical issues. So then what people do, and it works pretty well, is actually to define complex grid setup. So I think this MIT GCM, as used by Jonathan and Adam Schumann, as a cube sphere. So it's a bunching up together cubes on the sphere so that nothing special happens at the pole. People have yin-yang patterns. I mean, it's really complex grid so that you can deal with the poles decently. Spectral methods have the advantage that they don't have to do that. They tend to not scale very, very well at high resolution. On the other hand, they give pretty decent result even at low resolution. So there is a variety of pluses and minuses to each methods. It's nice to have these different approaches because, as you can guess, we don't have real information on what's going on in terms of atmospheric dynamics on exoplanets. So one of the things we have is comparison between different methods and trying to look for consistency. model intercomparisons play an important role in this business. And so again, the results I'm going to show you throughout the next few slides are basically taken from this MIT GCM, coming from MIT. PLACIM is from the University of Hamburg. FMS is a code from Princeton. LMD is a code from France. And then NCAR, CCM, CAM are actually codes that are made available as community code. I think they come from the National Center for Atmospheric Research. And all of these codes have been actually adapted to the study of exoplanets one way or another. And there's probably more going on, but this is an example of what's available. And so I just wanted to finish in one thing that I guess is worth emphasizing here, that I talked a lot about the atmospheric circulation. That's the topic of the lectures. But there is more to that that's going on in the atmosphere, of course. And so generally what we want is a full stack of the physics, relative physics, chemistry that's relevant to what's going on in the atmosphere. And so if you actually look at what's going on in one of these GCMs for the Earth, for instance, there you have this grid on which you follow the flow motions. But in each of the columns, you solve the relative transfer frequently, maybe not every time step, but like frequently enough as things change. And you spend also a lot of time for a terrestrial planet following what's going on in the planetary boundary layer, and specifically the exchange with the surface, whether you deposit snow and ice, to what extent you're able to actually mix heat and weather vapor from the atmosphere to the ocean and vice versa. So a lot of time a lot of effort is spent dealing with what so far I described as a boundary condition, actually. As boundary condition, the surface is actually quite important in a climate model. And a lot of extra physics is involved. What I'm going to show you now, I'm getting now to my second lecture, really, is basically applications of those type of climate models to exoplanets. And there's by and far what has been done is the following, especially to study hot Jupiters and warm near Neptunes. You don't care about having a ground and ocean and all this. So all that physics has been stripped, and then you just solve the things in 3D. You do keep the primitive equation of meteorology, so that's advection part. And then you solve the radiation at different degrees of complexity. You can use a simple relaxation schemes that are really idealized. Then you can use a gray relative transfer, and then pretty much the state of the art that has been done so far is using one of these K-correlated methods to compute opacities and solve multi-band relative transfer. By that it means, like, let's say you have 20 bands from the infrared to the optical, and you solve the relative transfer in those 20 spectral bands. And so that's pretty much, that's rather advanced. That's pretty much state of the art and what is done in even GCM for the Earth. But what is also done in the Earth is actually treatment of the clouds, the cloud dynamics, how actually you can condense particles and vect them with the circulation, dissipate the clouds if you change the thermodynamics of the fluid element. And that, to a large extent, has not been done for exoplanets. There is actually recent work on that, but this is clearly one of the areas of progress. So pretty much a lot of what I'm going to show you, with the exception of the result on Earth-like planet, is just solving the flow dynamics and the relative transfer, ignoring clouds. That's most of what has been done to date. Oh, actually, I'm sorry. And let me show you this. I guess I will make my slide available. A lot of what I've discussed can be collected and expanded considerably by looking at this. It's just a sample of references that I like personally. I really like the Vallis textbook on atmospheric dynamics. It also addresses ocean dynamics, but it's a really nice textbook to understand the principle of dynamics in atmospheres. I like the Pierre Bird textbook if you want to focus more on the radiation and chemistry. And then there's a couple of reviews that I recommend if you want to sort of follow what is being done specifically on exoplanets. . Is there any questions actually before I switch to the application? Any general question or? Yeah. We'll take your question after. Yeah. So I don't know if it's hard. What I said is maybe in some sense unnatural. It's you know, in thermodynamics, the heat flows from hot to cold. So similarly, you have an excess of momentum, a deficit there. A natural process like viscosity will tend to equilibrate this. So in some sense, it's not natural. How it happens in these atmospheres, I guess I will mention. I'll show you that it is seen in many of the simulations of exoplanets. And there is now actually a paper that has attempted, and I think successfully attempted, to explain why it happens. And the solution appears to be the shape of the forcing on tidal exoplanet is the key, I think. And so I'll mention that in this second lecture, yeah. I won't go into too much detail. It's a rather technical paper, but there seems to be an explanation behind the result emerging from the simulation. Jonathan, you had a question? Okay. Let me hide this. And here we go. So what I'm going to address in this lecture is basically 3 types of planets that are of interest. And I might, if there is time, even though I doubt there will be time, but I might address even a 4th type, the hot super-Earths. So those one I'll put aside for now. And I'll discuss hot Jupiters. Typical example of such a planet would be HD 209458b, 209458b. Warm mini Neptune, an archetype of that class is a JD1214b. And then planets, Earth-like planets around M dwarfs. And a typical planet of interest that has been recently discovered will be TRAPPIST-1c. That's a planet about the size of the Earth that received about the same flux as the Earth. So it's pretty interesting. I should say, you'll see that we have a fair amount of data, and I think you'll hear from maybe Jacobin more about this. I won't talk too much about the data. We have a fair amount of data and constraints on these planets, even though we do want much more in the JWST era, something that Jonathan has mentioned. We have some data on JD1214b that is constraining what's going on in the atmosphere, not so much the dynamics. And we have no data on those planets, but that doesn't stop us theorists and climate scientists to actually speculate about what sort of climate you might expect on those planets. It's a pretty interesting topic, I think. The key feature of all these planets that is related to the way astronomers find such planets is that we believe they're tidally locked. We believe they are in one-to-one spin-orbit resonance with their rotation. So astronomers in general, there are techniques now that tend to find distant planets, but a lot of the techniques that have been used, radial velocity and transit, to find extrasolar planets, they favor finding planets that are very close to their star. And that means they feel the tides. They have strong tidal interaction with their star. And so a natural outcome of that, even though I think there are possible complications there, but the natural outcome of that is actually a tidally locked configuration, like the moon to the Earth, where the planet is actually showing always the same face to its star. And so it means we are dealing with planets that are typically slowly rotating, because there are periods of a few days, maybe even slower. And they have a permanent day side and a permanent night side. And that's pretty interesting, because that's actually a more extreme regime than what we have in the solar system. The solar system planets the rotation modulates strongly the insolation so that you sort of equilibrate things in the sense of rotation around the sphere. But if you didn't have, let me take the example of an airless body. So imagine a terrestrial planet, let's say this guy here, that is very close to its star, and there is no atmosphere whatsoever. The temperature on the night side might be set by processes such as geothermal flux, and that would get you to extremely low temperature, tens of Kelvin maybe, or even less. So you could get thousands of Kelvin on the day side and tens of Kelvin on the night side. That's a pretty extreme situation, and extreme is interesting. And so I think what has driven people to some extent, I mean, by necessity, this is the planets that are being found, but also because it's an interesting regime that's different from what we see in the solar system, people have been interested in studying those planets and trying to understand what this special regime of forcing leads to. Hot Jupiters. So it's always good to go back to the basics first, and it's worth emphasizing that we are, in the sense of even a sense of a 1D average model of the structure of these planets, which might not be such a good model because the day side might be very different than the night side, but it's still very useful as a guide. We are very far away from a Jupiter-like structure. So what I'm showing here is one of Jonathan's results on this. Pressure in bar from about the photosphere here. So there's some slight differences of where the photosphere is located, where you absorb stellar light and where the infrared comes from. But it's about that region here, say, very broadly speaking. And so it's as a function of temperature, so it's a PT profile. The runoff temperature as you go deeper and deeper in the planet. And the solid lines highlight regions that are convective. And you go from, actually it's beyond Jupiter here, 10 AU, the blue, this is a distance in AU from a sun-like star, I believe. So you go from 10 AU, 5 is about Jupiter, and all the way down to 0.05 AU or 0.02 AU. 0.02 AU is really close, that's a really, really hot, hot Jupiter. And maybe a typical hot Jupiter might be this red line here. And what happens is that as you shine strongly on the atmosphere, but this is basically this body has about equal amount of flux coming out from the interior and actually from the insolation. This body here, actually interior flux is almost negligible for what happens in the atmosphere because you have orders of magnitude more insolation flux. And that actually strongly stabilizes the atmosphere so that you get a stably stratified atmosphere that goes all the way to hundreds of bars typically. And so we're dealing with a very, very deep atmosphere. This is not like Jupiter where you get the convection dome to appear just below the clouds that we see in the visible. This is actually a very, very deep atmosphere. And so I'm going to refer, because it's so deep in fact that you may want to distinguish two regions, and I'll use that in my description. One I'll call the weather layer. And the weather layer, I'm referring to the region where basically you actually force the planets with insolation. So this region here, up to maybe a few bars at most, is where you're able to deposit some of the solar insolation. But below that, it's basically inert. It's actually a stably stratified atmosphere, but there is none of the solar radiation that comes and actually force any of what's going on here. So it's a slab of atmosphere that's really not thermally driven. What happens to it is probably through a coupling to the convection dome and through a coupling to the atmospheric layer on top. And it's somewhat of an unknown to us actually what's really happening there. So it's a rather interesting region for future progress. So we're dealing with very deep atmospheres. And so I'm just showing you an example. It's pretty old simulation from the early days of what do you get now if you set up such a hot Jupiter on the computer. So you take one of these Earth-based GCM, you modify it so that you get the right radius of the planet, surface gravity, you set up a deep atmosphere, and then you shine on it in a way that's decently close to what we expect is going on, assuming the planet is steadily locked. So one-to-one spin orbit resonance. So it's a permanent day side, permanent night side. And what do you get? Well, you get different regimes of flow from 2.5 millibars all the way to a few bars. I guess I should emphasize here, I didn't give you the number, but this 0.1 bar here, which is 100 millibar, is a typical region where you are in between the optical photosphere, so where you actually start absorbing a good fraction of the solar insolation, and then the thermal photosphere. Typically, you keep absorbing down to maybe 1 bar. So this region around here is where you force, and also where the infrared photosphere, where the planet irradiates, is located around these levels, you know, between 1 bar and 0.1 bar. 100 millibar is a good number to keep in mind. So this slide is showing you above this 100 millibar, around 100 millibar, and deeper in the atmosphere, what's going on, okay? So this is more like closer to this inert layer. This is a weather layer. And so look at the temperatures. Oh, I should say that the central region here is a substellar point. That's where you shine the most. And you get temperatures. This is actually, you might notice noise here. This is numerical noise, probably, a defect of that simulation. This regime is not easy to simulate well. But what you do get is actually basically a temperature pattern in the atmosphere that follows the insolation. From a maximum on the day side of about 1700 Kelvin all the way to 240 K, very, very cold on the night side. So really extreme temperature differential here. You actually are driving winds, in fact, very fast winds in these upper layers of hot Jupiter's atmosphere, but those winds are unable to advect efficiently the heat. And the reason that is because the thermal response time of the atmosphere in these very tenuous layers is actually very fast. One way to understanding that is that you have a relative response time that's shorter than the advection time, the time when it would take you to actually advect some of the heat away from the day side to the night side. So basically, there are winds, but they don't do much. It's basically a relatively forced atmosphere, and you see the shining pattern. As you go further down, however, you get denser gas that's better able to advect heat away from the hot day side, and you get actually a relative response time of the atmosphere that gets longer and longer. So you see more and more the role of advection. And you might see this sort of, I don't know if it's very clear, but actually, basically there's a lot of arrows here that points in this direction, which is eastward. So you actually, around the equator, you have a coherent flow going in a positive eastward direction. And that's a super rotation I was mentioning before. And then, so you basically modify the temperature pattern a little bit by actually advecting it away from the substellar point. And then when you go further down in the atmosphere, the winds are much weaker, and you get a pattern that's rather different. And I won't emphasize too much what's happening here because it's not necessarily of direct interest to observations, but we could spend more time on this. So wind speeds, remember my table with wind speeds of 20 meters per second, 200 meters per second, right? Now we're in kilometers per second. This has extremely fast wind speed. In fact, they're so fast that it's uncomfortable. The speed of sound in this gas is like, let's say, 2,000 meters per second. 2 kilometers per second is a good scale, okay? So the wind speeds here are supersonic. Even here, they're supersonic at the photosphere. And they become supersonic as you go further down in the atmosphere. Now, this raises like warnings because you might remember that I justified going to primitive equations for slow subsonic motion. That's one of our assumptions. So we're using equations that assume, by construction, subsonic motion, but they deliver supersonic motions in this atmosphere. So that's something that may be worth discussing a bit further in the third lecture tomorrow as a point of worry. And so there has been a fair amount of work over the years. Now this has been going on for a good half a decade or more. And the good news, I should say, my goal today is to give you the rosy picture. That is, we can solve this equation for exoplanets, we get results, and in fact we see some evidence for those results being validated by observation, which is definitely a success. But then we get to the gossip of what we're not happy with next lecture. There's a number of things that we might want to worry about and we don't fully understand. And so these are interesting topics for further work. And so people have tried modeling these hot Jupiter flows using different solvers and different approaches. And I think Jonathan mentioned some of this. So this, I think, is a grid-based model. This is a spectral model. This I think, is from Dobbs-Dixon. That's actually this protoplanetary disk model that has been extended in sort of a non-trivial way. One of the advantages of that model over this other is that it is fully compressible hydrodynamics. So actually, it's more general in its treatment of hydrodynamics than actually the GCMs. This one, I don't remember where it comes from. This is actually, I think, your work with Adam Schaumann. This looks like one of those pictures. And this may be from Schaumann and Paul Vanni, I think, one of this simplified model. That's right, yeah. That's showing actually a very simplified model being able to reproduce the regime of circulation satisfactorily. And so that's basically the justification behind my claim that we now think we have some understanding of what's going on here in this atmosphere using a very simplified model that reproduces this more complex model. So the point being here that the rosy picture for now, we're going to stick to that, is that various modeling approaches show consistency at the qualitative level for sure and at even some quantitative level. But there are differences, you know, where the wind speed can differ by a good 30% from one simulation to another simulation. So certainly we know that these areas of improvements to be made. Yeah.
When you say compressible, I mean, ECM, the continuity equation is compressible, but you mean does it erode?
I mean, it's sort of Navier-Stokes, so it's not filtered sound waves. Like you, in GCM, in primitive equation, you filter these sound waves, right? Because you assume hydrostatic balance. This is an unfiltered sound wave. So he has the whole spectrum of sound waves that you can get. And that's important because of the supersonic winds. That I think sound waves, I'll get to that tomorrow, I think. This is an important feature that we probably want to have for those flows, yeah. Yeah, so this model that you heard from what Jonathan has been doing with Adam Schaumann and the group is better, for instance, in the way it treats a radiative transfer. It's clearly superior in that way. You can get decent result by using gray or even simplified radiative transfer. I think going to a GCM is still the good way to go. There are advantages. So there are a number of features maybe in this flow that look a little bit odd and not consistent with GCM results. So it seems to me that GCM is still the way to go. And because this is a very deep atmosphere, you need multiple layers. So I don't think there's really a way around that. But there are open problems, something again I'll emphasize more tomorrow, that it would be nice to be able to do a compressible, and in fact it would be nice to be able to do the MHD. I'll just like, this is getting really complicated. The compressible MHD on the sphere, it would be actually maybe what's needed to really nail that problem. And this, as far as I know, does not exist in terms of a solver. Was there a question? Yeah. Yeah, so that's right. So it depends what you're after. If you just want to get a basic dynamical regime that's similar, then that's fine. If you want to start addressing observations, then you need the depth and some radiative transfer, right? And so that's why people tend to go to that, because we have done the basic, well, not maybe all of it, but we have addressed some of the basic atmospheric dynamics. And what's interesting with the hot Jupiter is that there is actually data that you can compare to, I think. So people do go to GCM with depth for that reason. Yeah. So it's just a slide summarizing sort of what has been done in terms of hot Jupiters. How am I doing on time? Oh, all right. So there's, I would say, a fairly extensive modeling literature on this type of planets. And one of the things that's pretty nice compared to actually other exoplanets is that we have a rough idea of what the composition is. And that might seem crazy to some people from planetary science when I say that. But the point is that it's an atmosphere that's mostly made of hydrogen and helium, molecular hydrogen and helium. And then maybe it's solar composition, maybe it's twice solar composition, maybe it's 3 times solar composition. That will matter. That will change the opacity, that will change a number of things. But certainly at the quantitative level, people have tried varying that, and it doesn't dramatically change the atmospheric flow and what's going on there. I guess one area that is still not clear is if you were to put clouds. This is an area where things might become very nonlinear, and then the actual detailed composition might matter. So that I think we don't know the answer to. But it's a good position to be in comparison to actually the other thing I'll show you on which is modeling that's been done, which is the warm mini Neptune or super Earth, where the composition is totally unknown, and that leads actually to a number of complexities. And so broadly, people have seen supersonic winds emerge, and rather consistently, people have seen this super rotating circulation regime emerge. I'll show you a zonal wind pattern now. I think one of the things I'll emphasize is the fact that, generally speaking, the most advanced models that have been done have been actually successful to a good extent at reproducing infrared phase curves, so actual observational data, and I'll show you what I mean by that just in one slide. And then there is, of course, the big elephant in the room here, clouds in the circulation models. Very little has been done still to this day. It's a difficult problem. But I'd like to show you, it's clearly a key area of improvement. There are some results. I won't actually discuss them in my slides too much. For hot Jupiter, there's a very nice result for JG1214b that came recently. And so that I'll show you one result of an actual GCM with clouds for exoplanets. So this is a zonal wind pattern. So it's a summary of what the atmospheric flow is, if you will, in these planets. This is the pressure in bars. So again, you know, the optical absorption and infrared photosphere might be typically located around this 100 millibar level, around it like this. And the model you see going down to, in that case, 200 bar. So approaching where we believe the convection zone might be. And again, these weather layers, so that's a layer that's actually actively forced by solar insolation, and these deep layers that are actually not being forced. And they happen, even though they're passive, they might play a big role they might play a significant role in what's happening. And what's the meaning of is this plot done? You take the zonal winds, what's called zonal wind speed. Zonal means east-west. I mean, the people who know about this is obvious, but some people might not know, so I just want to make sure we are. Zonal means axisymmetric, so it's along a latitude circle. So it's the east-west speed. Positive means you go east in the sense of rotation. Negative means you go west in the opposite sense of direction. You do an average along each latitude circle. And then you do that as a function of pressure and latitude, equator, South Pole, North Pole. And so the equator is here, and you see that throughout the weather layer, this layer that's being forced by the solar insolation, you have actually strong positive winds, so you have equatorial superrotation. And again, that's been seen to emerge consistently. And then you do get negative winds approaching the poles here, high up in the atmosphere. I think that's sort of seen also rather consistently. And I'll have you notice that there is this area here of negative winds. You see they're blue, so they're negative winds. So you remember I told you superrotation means you pump up angular momentum where there is already a maximum. Now, the way we treat this simulation and this atmosphere is that this is a finite box of atmospheric gas, and at the top there is no exchange of angular momentum or mass. At the bottom, there is no exchange of angular momentum or mass. It's a free slip. You know, there is no surface, so we don't put drag. So it's a free slip boundary condition. It's a material boundary. Nothing crosses it. And so what it means here is that in that volume, angular momentum is conserved to machine precision, to the extent that you have coded the equations well, right? Angular momentum is conserved. So when you pump up angular momentum here, it has to come from somewhere. It appears, even though I don't think that has been diagnosed really as much as we would want to, it appears that the angular momentum that is pumping up this jet here might be coming from this layer below, because you see this negative wind velocities here. And so there might be somehow a form of exchange here that we have not fully understood. My point being, I suppose that this deep inner layer that you might not think as being too important, they're actually a huge reservoir of angular momentum, and they might play a role, and there is some coupling between these layers. Yeah. No drag whatsoever. Yeah. So this specifically is Newtonian cooling. I think it was a Newtonian cooling simulation, and so it is not convecting. As far as I know, there is no need for convective adjustment. Yeah. And so I think Jonathan might comment if whether in when they do the relative transfer better, they might get some columns to be convective. I suppose it's possible, but in my experience, we don't find convection to develop in any of the columns. It is driven by relative transfer, but what I'm trying to say is that nowhere in the evolution do you get a column to develop convection. And I'm referring to dry convection, because really you would want to do moist, but we just do dry here. Yeah. So they don't get to be convective. They are very stably stratified atmosphere. Another question? Say that again? This is primitive equation, so it's asymptotically balanced, yeah. And so I was telling you it emerges consistently. I think a demonstration of that is actually from this paper by Kataria and collaborators, where they look at 9 hot Jupiters from equilibrium temperature of 1000 to 2000 Kelvin. They go here in order of hotter and hotter and hotter. So basically you have a more weakly insulated hot Jupiter going to a more strongly insulated hot Jupiter. And you can see that the pattern is consistently you get this super-rotating jet that's emerging, and you get stronger wind speeds for more strongly irradiated hot Jupiters. And so this super-rotating regime is actually understood, or at least the explanation that's out there, and I think it's a pretty good one, is that there is a wave-mean flow interaction, and then I think at the end, it boils down to actually the nature of the forcing. Being large scales and having this day-side forcing is actually lead to this strong wave mean flow interaction. And this type of interaction has been shown actually to, in a very simplified 1+1 model, to actually lead to this super rotating regime. So I think most people in the community believe that's the explanation for what's going on. Sorry? So it's referred to as a standing Rossby wave. So I suppose it's a Rossby mode and it's excited from the shape of the forcing, the globally atmospheric shape of the relative forcing. Of course, we know of planets that are not actually necessarily tidally locked, and in fact, something I didn't say, we know of a lot of exoplanets, and there are interesting ones on which you might want to generalize things. For instance, planets that are actually not necessarily tidally locked and have finite eccentricity orbits. And you might wonder whether things change dramatically in that case, and actually that doesn't appear to be the case. So this super rotating regime that I've just described and showed you 9 examples of is actually still maintained to a large extent without strong modification, even for a planet like HAT-P2b with an eccentricity of 0.5. The atmosphere cools down as you go to apoapse, heats up as you go to periapse, but actually the atmospheric flow itself tends to be in the same regime of super rotation, equatorial super rotation. So it seems to be a really an attractor, if you will, something that's really a result that's coming out solidly from simulations of a variety of hot exoplanets, even when they're eccentric. My guess is that the tidal heating would be, but there's a question of where you deposit that heating first. So it might be deposited interior, and then it might contribute to the interior flux somewhat, but it might not be, you know, the solar insolation is very large. I suppose when you're far away here, maybe in some extreme case, you might want to account for it. I'm not sure it's really a dominant term, yeah. But you're right, that there would be tidal heating, yeah. Okay, so maybe what is arguably the biggest success of that enterprise of trying to understand the atmospheric flow on hot Jupiter has been the ability to qualitatively and to some extent quantitatively reproduce infrared phase curves. So I just pick one example here. I think there might be even better matches to HD 189, another hot Jupiter. This is HD 209458b. Again, it's coming from the work of the group of Adam Schumann and Jonathan here. And what you see is one of those phase curves that Jonathan described in the first day of the conference. So what you observe is the amount of infrared light that's coming from this hot Jupiter as it goes around its star. And you expect the modulation, hot day side, you get more infrared. Then when you see the night side, you get less infrared. And you get to see the secondary eclipses and the transit. And something that has been noticed, we have several phase curves like this now. I don't remember exactly how, maybe half a dozen, something like that. And then something that has been noticed almost consistently, there is an exception, is that the peak emission, infrared emission, precedes the secondary eclipse by a few tens of degrees. And so that is, the planet is hottest a little bit eastward of the substellar point. And that is what is coming out of the simulation. So let me show you this map again. So I have to go back. But all these things, because of the equatorial superrotation, you advect the heat away towards the east. And then you expect the peak infrared emission to peak somewhat before the secondary eclipse. This, maybe to emphasize the significance, this was predicted before it was seen. So it's rare in astrophysics that we get to predict things before they're seen. But it really actually was. And so now, using, I think, the most advanced model out there from using this Spark MIT GCM, this group is able to actually fit this infrared phase curve, getting about the right time at which you get the max of infrared emission. And in this case, at least, they overpredict the amount of emission on the night side. This might be related to the formation of clouds on the night side. I think there's a very real possibility that could actually explain this. There is no cloud in this model. The night side is cold. You might expect clouds to form that could reduce infrared emission. So that might be what's going on here. But by and far, it's actually, let's say it's consistent with what the simulation of hot Jupiter atmospheric flow predicts. So there is actually a success story out there. And yeah. This is multi-wavelength. This is how many bands do you have? 20 bands? Yes. This has been measured. This is just 4.5 micron, but we have phase curve at different wave bands, and the model, I would say, does a decent or good job. It depends on your point of view. It actually does a decent job at predicting the different phase curves in different wave bands. Yeah. Yeah. So it's working. It's really encouraging. It's working like you get it seems like the basics are actually are there. Now there's one exception. There's one phase curve that looks very different in where the peak emission is by maybe 90 degrees or more. I think, is it 51 peg? Oh yeah, Upsilon Andromeda, thank you, yeah. So there's one phase curve that looks very different from the others, and none of the model is able to actually explain that. I suppose the feeling for now in the community that this is an odd planet. Somehow something odd is going on there that we don't understand. It's not transiting, that's right, yeah. So there's something we don't understand, but consistently for several planets, the models do predict things and observations seem to confirm them. So this is basically the end of my section on hot Jupiters. And we are leaving now the area where we have been able to compare semi-directly, if you know that, I would say is a pretty good, is as good as it gets. We have been able to compare the prediction of models of atmospheric circulation to actually observational data points. And by and large, this has been done, almost exclusively, I would say this has been done with, for hot Jupiters. There's a lot of planets out there that are very interesting, the so-called mini Neptunes or super Earths, that people started modeling. But we are still lacking phase curves and sort of diagnostics that are really constraining for the atmospheric circulation. But the models are there, so we're starting to get an idea of what's going on. So let me just develop that story a little bit. And the archetype, I guess, of that class is JG1214b, so it's a specific mini Neptunes. And by far, you want to think about these planets have been modeled exactly like hot Jupiters, you know, a deep atmosphere I mean, you do put in the right rotation rate, assuming it's steadily locked. You do put in the right TP profile, this sort of thing. But it's basically a deep atmosphere, and then you shine on it the way you think the system is forced and try to see what emerges. And, but one of the issues you have, I mean, several people in the room here, Jonathan, Diana Valencia, Eric Lopez, a number of people here have worked on this problem. The main issue we have with this type of planets is that given a mass and radius, we can't quite tell what the composition is. We know hot Jupiters have to be basically hydrogen and helium, made of hydrogen and helium with some core or not. But these planets, we don't know. They could be made of hydrogen or helium. It depends on which planets. You know, there are constraints. But basically, we have planets for which we don't know if the atmosphere is Jupiter-like, hydrogen and helium, or maybe if it's dominated by water, or maybe it's dominated by CO2. All of that is actually a possibility. You can basically build that planet in different ways and get this right mass and the right radius. And so then an interesting topic for atmospheric modelers is like, can you actually use the atmospheric circulation to discriminate? Is it possible that if you model the atmospheric dynamics of molecular hydrogen atmosphere or a water atmosphere or a CO2 atmosphere, you actually will get different circulation regime or different observables you could use to discriminate between these possibilities. And so what has been sort of established, I'll show you some results briefly, is that the composition actually does affect the circulation. It does it through essentially two ways. One is mean molecular weight. H2 is a very different mean molecular weight than water, for instance. And that has some effect on the behavior, specifically the radiative behavior of the atmosphere. And mostly, I think the dominant effect is opacities. You change, by changing the opacities for changing the composition, you change the depth at which your absorption of insolation happens, and also your infrared emission happens. And that actually tends to strongly affect the observables that I showed you in terms of the phase curve. So I think this is something that's been sort of established nicely. It's not been observed yet, but it has been established as a potentially strong discriminant for what the atmosphere is made of. So this is an example of this few slides are an example of actually theoretical work potentially leading to observation that might help us discriminate between different compositions. So here is an example of TP profiles. I think they're simplified TP profiles, but they make the point. For JG1214b, you see there is a CO2, water, a mix of CO2 and water, hydrogen, helium with 1 time solar composition for the metals, 30 times and 50 solar. And the point here is that look at this scale. You know, this scale is actually quite large. So here I have 1 bar, and here I have 10 millibar. And so if you look at, for instance, the difference between 1 time solar and water, so green is water, 1 time solar is this pink dash line here, you get a very, very significant change in the depth of where you, this is the infrared photosphere, basically. This kink here is basically the tracer of the infrared photosphere by a factor of maybe 5 in pressure. Almost an order of magnitude, and you maybe get also almost an order of magnitude for the depth at which you absorb solar insolation. And so then the density of the gas at the infrared photosphere is changed. The radiative response time of the gas at the infrared photosphere is changed by having this, this deeper or less deep in the atmosphere. And so as a result of this, something that I tried a few years ago with just a very simplified gray radiative transfer. As a result of this, the same planet, the exact same configuration, just changing the composition, so just changing the mean molecular weight and the opacities, will get you a strongly modulated phase curve if you have water, atmosphere, and a rather weakly modulated phase curve if you have solar composition. So that was an indication that composition will offer you a strong discriminant in phase curve. Since then, this has been done much better using this multispectral code. And so I think, again, Tiffany Kataria and collaborators have basically shown that you are able to discriminate, you should be able to discriminate the composition in the atmosphere or JG1214b, and I think more generally mini-Neptunes, super-Earth, by using infrared phase curve, if you're able to get infrared phase curve. So for instance, so their plot is there's a lot of information in this plot. But I can maybe point to this D band here, which I guess is 4.5 micron. Is it? 1, 2, 3, 4. Oh, okay. So let's focus on this D here. This feature, you see the different colors of lines of colors here correspond to different phases. So where you look at the planet on its orbit. And so basically, if you stick at this wavelength here and look at the planet, you see a strong modulation of the phase curve. It goes up and down as it goes along the orbit. So something like that for water. And then in this 50 times solar case, the same spectral band, you see very little modulation of the phase curve, so a much flatter phase curve. So it's basically a consistency between these two results, even though that's probably a much better way of doing it. That suggests that if you get an infrared phase curve for something like JG1214b, the circulation will tell you what the atmosphere is made of, which is, I think, a rather nice result. Yeah. I think JWST. But now, you know, if you talk to the observers in this room, like say Jacobin, for instance, they'll tell you, yeah, but you don't have clouds. You don't have clouds, and we have established, I mean, the observers have essentially established that from transmission spectroscopy, and you'll hear a lot about this, I think, that looking at how light, the nature of the light going through the atmosphere, the stellar light going through the atmosphere, that there appears, for this planet in particular, there appears to be a haze high up in the atmosphere or a cloud layer that actually damps all the absorption feature you would otherwise expect. And so there are clouds out there. So maybe all this business, all this modeling, very idealized without cloud, is actually not quite relevant once you have cloud. And so a very nice result, I think, that came out just a few months ago from this Charney et al. People using this LMD code, which is a very nice code in a number of ways. What they have shown is basically, I would say, a point of principle. They have what might be a consistent model for JG1214b. By that I mean that they have a type of cloud, KCl, what is it, like potassium chloride? Okay, potassium chloride clouds. They have to specify a size for the cloud particles. You know, the cloud formation is complex, so you have to, in their model, you have to specify a size. That size is most important to determine the optical scattering properties of the clouds, I think. And these are clouds that are dynamical. They are clouds that are advected, formed, and destroyed in the atmosphere following the dynamics. And actually, they do scatter light. They do actually affect the radiative transfer. So these are real clouds. Well, people who do clouds for the Earth might have an issue with me saying that. It's still a simple model of cloud. But this is actually modeling clouds in a dynamical context for JG1214b. And they are able to get, for this one case, it doesn't mean that's what's going on, but I think it's a nice point of demonstration, that for this type of cloud, you get actually to find them to be close to the poles. You see this is a mixing ratio, so in red it's high, in blue it's low. There's not so many clouds around the equator, more clouds around the pole. The circulation regime is, you see this jet here going eastward, again, super rotating, so everything stays the same as before. And then they compute a transmission spectrum, and this is their blue and red line are the model. These dots with error bars are the data. This relatively flat spectrum here that suggests there is a cloud layer. So the model is consistent with the observation of the transmission spectrum. And when they now predict infrared phase curves from that model, they still get the type of modulation that is highlighted in this on this model. So the point being that even with clouds now for JG1214b, the basically transmission spectra has been a great tool for hot Jupiters, but when there are clouds, basically they can become useless in the sense that we don't quite know what's going on in terms of what's the composition of the atmosphere. Then maybe atmospheric dynamics will come to the rescue. If you get a phase curve, you should get a very different result whether you get water or a Jupiter-type hydrogen-helium atmosphere. So this is the story that's developing, and we'll see how it plays out. Yeah, I think that's true, but it's also that the clouds have, so the clouds, what they do is that they scatter optical light. So certainly in the optical, they do change what you see a lot. But those clouds of those particles, they are optically thin above 3 micron because of their sizes. So actually, it means that in the infrared, they become transparent, so they don't affect so much what you see. So I think that's the main reason, that they become, this is sort of a thin layer of cloud that is enough to explain what you see in the optical and not modify things strongly in the infrared. So again, it's a point of principle. They just found a solution. Who knows whether these are the clouds that are actually on those planets? But in principle, you have a handle on what's going on using the infrared phase curve and the circulation. So we'll see. It's quite an achievement, I should say, technically, to actually run such a model in that regime and getting the clouds to, your model not to crash. I can comment on this further, but okay. And so I'm sort of, as I expected, my lecture 2 is probably going to get into a little bit to go over to lecture 3 tomorrow, but I can keep going for a little bit. Yeah. So now we go even beyond the realm of data. This is pure theory speculation, but it's actually quite interesting, I think. Trying to understand what might be going on exotic version of the Earth. So this TRAPPIST 1c planet is a good example. It's a planet of the size of the Earth that has been found around an M dwarf star, so a very low mass star. And so as a result, the habitable zone, where you get about the right amount of insolation to get liquid water at the surface if your atmosphere is that of the Earth, more or less, that happens to be very close to the star. And as a result, we are fairly confident for those planets that they should be tidally locked. Given the age of the system, it takes a short amount of time for a rocky body to get tidally locked. And so now you have an Earth-like planet that's rotating slowly. Again, actually, I don't know the rotation period of that one specifically, but it tends to be a slowly rotating planet with a permanent day side and permanent night side. And that's pretty interesting, because what would be the climate on such a planet? You know, where would it be habitable? Do you get too hot on the day side, too cold on the night side? You can only live on the terminator. You have liquid water only on the terminator, or what's going on? So for maybe a decade now, but things have been going more actively in the last few years. I think people like me, but also actually climate scientists have gotten interested in trying to understand the climates on these planets. And again, one of the drivers is like this day side, night side, and what it might imply for an exotic climate. So there has been a fair amount of publication on this, and I will just highlight maybe just one result in the interest of time. And so again, people have found that you get this super rotating regime to emerge in many of those simulations, even though they're terrestrial planets. One of the, I'll just go through these few items quickly. One of the things that has been established is this as a possibility for the climate on such planets. So if you take an ocean world, a planet totally covered by water, no continent, and then you try to simulate the climate, tidally locked, then I think Ray Pierre were the first one actually to get one of those GCMs running and publishing it. And he termed that the climate that he got an eyeball, and the eyeball climate is this. You get like open ocean facing the star, and then a huge ice sheet, you know, at the terminator and on the night side. So you get a climate that's actually interesting and odd in some sense. And then people have revisited this, showing that actually the ocean transport, the ability of ocean to transport heat in that climate is actually quite important to get it right, which was not included in Pierre Imbert's first paper, I think. People have been interested in those climates because of what they call atmospheric collapse. This is the sense of my question, you know. People have said, for instance, let's say we only have CO2, like Venus and Mars. I mean, you have other things, but let's say you just have CO2 as an idealized case. And then the atmosphere is relatively thin. Then it is not going to be able to very efficiently necessarily carry the heat from the day side to the night side. So you might have very cold temperature on the night side, so cold that you condense CO2. So now what you have is Mars, because Mars condenses part of its atmosphere at its pole, the CO2 atmosphere, and it does that seasonally. But here what you would get is actually an amount of atmosphere after collapse that's set by the coldest temperature on the planet, which is on the night side, presumably. And so you could get to have a very thin atmosphere. And in that case, it might not be habitable. I guess I should say one of the things that's driving these studies is trying to find the limits of climate that might be habitable versus not habitable. And so this business of atmospheric collapse is interesting because in the limit of relatively thin atmospheres, you get the whole atmosphere potentially to collapse. Even the dominant CO2, which is a strong greenhouse effect gas, is not enough to actually maintain a sizable atmosphere, and then you get to be in the very thin regime, and things may be quite bad for habitability. People have sort of discussed ways of extending the habitable zone. And in the Chicago group, Dorian was involved with that, as shown, for instance, that you might have a region that's a bit special on the day side, and I'm going to show you one such result here. You might have a region on the day side where actually you're able to form a lot of clouds that are very reflective. And so effectively, you're able to push the limit of the habitable zone because you have a huge albedo on the day side, so you can bring your planet even closer, about twice the flux of the Earth, I think, in some of the simulation. You can bring the planet closer without it being evaporating the ocean, if you will. And so again, that's the key driver here is that the day-night forcing is very different. It's a very different regime than what it happens on the Earth and the solar system planet. And so there are things to be understood about what that regime does. I'm going to skip this issue of climate stability, which is interesting in itself. I should say, M dwarfs are variable. So actually, something that I like is that this group, Joshi et al., worried about flares from M dwarfs actually affecting the climate strongly. And I think this, they have done a study. I think we're not yet done understanding all of what the flares. There's huge luminosity variations from these M dwarfs from having a large star spot, and this could actually affect the climate strongly. And so one of the things that I got interested in, and also the Chicago group has done work on, sort of looking at this, again, at this eyeball climate, one of the things that sort of popped up here, it's sort of obvious, is that sure, this is what would happen if you have abundant amount of water. But what if you had not so much water? Then actually you have a tendency to condensate your water, snow on the night side, and then what Joshi realized, mentioned in his paper in 97 here, no, in 203, sorry, it was the second paper, he mentioned a rate of snowfall on the night side, and they are not that huge, but over millions of years, the consequence would be that kilometers of ocean would evaporate and pile up on the night side. So on a planet where you would not have as abundant amount of water maybe as the Earth, you might imagine a climate that's actually not so good maybe for habitability, where you take all the water you had on the day side, you evaporated it, circulation carried this weather vapor, then you snow it on the night side, and you have a huge ice sheet on the night side, and then maybe very little liquid water available. Again, this happened on the Earth at the pole, but the area, surface area, basically that we have, and we pile up on the ice sheets, the amount of water in the ice sheet is relatively small. The point here is that you could have a large ice sheet on the night side, and it could trap water. And so again, the Chicago group revisited this and showed actually for this really to happen, you probably need special conditions in the sense that you need a continent, a large continent on the night side. Because if you have ocean basins on the ice side, water will flow, and the ocean is good at actually carrying heat from the day side to the night side, and it prevents you from piling up a large ice sheet. So in other words, they do get here, this is the amount of sea ice over ocean. They do get in some cases, I guess on the ocean, they only get like tens of meters. They only are able to get kilometers, you see 3,000 meters, kilometers of ice on the continent. So you could trap a lot of water on the night side, but you probably need a big continent there. So what I'm trying to illustrate here with this a few slides is that we sort of know the Earth's climate problem is rich and complex. When you get to actually exoplanets, there's even more interesting things that are happening. It's a very rich problem, and so people are sort of exploring from a theoretical point of view what might be happening, what sort of climates we might achieve on those planets. And if anything, this might be a good guide as to what we might find in terms of habitable or non-habitable planets when we start discovering more of this and characterizing more of these Earth-like planets around M dwarfs, which are a priority of astronomers in terms of searches. So I'll just conclude with that slide saying that clearly we see a lot of diversity at work here, a lot of surprises, a lot of things that we don't understand, but people are modeling the atmospheric circulation of exoplanets and achieving some success.
For the gas giants, where you can have surface gravities that can differ by a factor of 100 or maybe even 1,000, from like a fluffy Saturn to like a little brown dwarf, to what degree would surface gravity play an important role in Rhine's length or just any sort of length?
Yeah, I've wondered about this and I don't have a good answer. But I think it might matter, yes. And I don't know that. I don't know if you guys have done a parameter survey of this. I have actually not tried to systematically study this, but it looked like it could matter, yes. Yeah, buoyancy, basically the Bryan bicycle frequency is, the n I had in my formula is typically g over h, right, as a scale. So it would matter that way. But it matters in a number of ways, so it's hard to know how it will play out exactly. I mean, I suppose you do have some answers to that in your work, this work, right? Yeah. Because there's some G variation here, probably a factor of 10 or more, right? And it's not dramatically affecting the circulation. Yeah. No, I think the G does matter for the dynamics. Okay, so this was a rosy picture today, and we'll get to discuss a lot of the issues or potential issues tomorrow, and this is one of them. So I can give you a partial answer. You'll notice that all of them, like the one I showed you before, are these negative winds just below the forcing layer. So I did mention that it's quite possible that what is pumping up, because you have a finite amount of angular momentum that's conserved in that box, that what actually is happening is somehow you're able to take that angular momentum here and give it to the superrotating jet. I don't know that I have a proof of that, but it's certainly a possibility. And so now people, like I have tried, and I'm sure you guys have tried, changing the size of the, where you put the bottom boundary. And the atmosphere is so strongly forced here that actually it doesn't seem to strongly affect the dynamical regime. So that at least we checked. But there are still issues, and I'll elaborate on those maybe tomorrow.